Okay. Let's go slide 28 here. We're going to look at phase changes. I don't know why they don't call them state changes, because that's what you're doing. You're changing from one state of matter to another. But phase changes is more typical that you'll hear. So when a change in temperature happens, that is usually the number one way that you get something to change from one state of matter to another. It's overcoming kind of the attraction between the molecules. It's not a bond. So if you're thinking water, it's not like the hydrogen separates from the H2O or the O separates from the two H's. When we say an attraction between molecules, that water molecule itself is intact. But how attracted is it to the other ones? That's what we're talking about. Okay, so one of the Kahoot questions worded it like this, and a few of you are like, what? Like throughout the day. We haven't talked about the attraction, so that's probably why that question maybe was a little bit, like, it was the best answer for sure. There's some odd ones, but, you know, we haven't necessarily said, hey, these molecules are attractive, and that's why they're together as a solid, and then they spread apart more when they're heated up as a liquid, and then they spread really apart. So the farther apart they are, the less attraction there is. And so it's kind of worded that way sometimes, so just kind of want to point that out. In the middle of a phase change, or in a phase change period at all, I guess, two phases are actually present. Because let's think about it. You instantly, usually besides like that video we watched yesterday with the hot water turning to the ice crystals immediately, usually there is a period where you have some of the solid and you have some of the liquid, or some of the gas and some of the liquid. So like when I was boiling that Kool-Aid solution, I had some of my liquid boiling, but I could also feel some of it being turned to steam and collecting on the bottom of my hand, right? So both phases were present, a gas and the liquid, for a while, until all of the gas or all of the water was evaporated off, and then it was just gas in the air, right? So during a phase change, two phases are present, okay? And so that's going to be something we're going to see on these graphs in the next couple days. So here are some examples. These are vocab words. You have heard them. We've been using them. Obviously, melting and freezing, I think you guys got. No problem there. I've even heard you correctly use evaporation. Condensation is usually a little bit harder to get. Do you guys remember the water cycle song that you probably learned in elementary? Evaporation, condensation, precipitation to the ground. Yeah? No? No. So maybe you guys didn't. I think it was a teacher that's no longer here. Maybe you guys did not have him. But he, like, for years, everyone was always like, oh, it's like the water cycle song. So he must have, like, hammered that in their head, but you guys must not have him. Anyways, it's the same thing whenever you think of condensation or evaporation. This is the same process as that. All right, so whether you're talking water cycle, whether you're talking like the little sweat beads that form on a can, that a cold can in a warm room or a room temperature, air temperature room, like that is the same process. So we're not adding anything new. You guys have known this. Hey, make sure you're paying attention up here. It's the same process. Now, sublimation and deposition are probably two new things that you might not be super familiar with. When we get to these in particular, we'll cover those, and they'll be a little bit more, hopefully they'll make a little bit more sense. So we know the solids are going to look like this. The water molecules don't have as much attraction. They're not tightly packed. And then the gas are the wild child, right? They're moving all around. So when you go from the solid to liquid, you're going to have a period where you have both solid and liquid. When you go from a liquid to a gas, you're going to have a period where you see both of those, right? And then we can also go the opposite direction. If things are getting colder following the blue arrow, we can go from a gas back to a liquid, and then from a liquid back to a solid, right? So it's whether you're adding thermal energy going this direction or whether you're taking thermal energy away, cooling it off, if you follow that blue arrow going up. Here's another way to look at it. We have our states, and then notice that the arrows going up are showing the heating up process, going from solid to a liquid, the melting, a liquid to a gas, which we call vaporization. Vaporization is really just, it has two forms. It can happen through normal evaporation, like at the surface level, or evaporation because you're boiling something. So if you see vaporization and you're like, wait a minute, why isn't that evaporation? It kind of fits under that vaporization heading, right? And so as you notice, these are heating up. If you go this direction, it's cooling down. Heat is leaving, or it is exiting, which is exothermic. Heat is entering, which is endothermic, taking heat in. Notice off to the sides, we have sublimation and deposition. Well, sublimation goes straight from a solid to a gas, and deposition is the opposite, a gas straight to a solid. And again, we'll look at those in more detail here in the next few days. So when two phases are present, like a solid and a liquid, that's an indication that a phase change is taking place, okay? If there's just one phase, then it's just not going through a change. So here you can visibly see two states. I see gas and I also see the liquid. So this is undergoing a phase change. All right, so melting. Start with the easy ones. Solid changing to a liquid. You're adding thermal energy, which increases the temperature, which increases the kinetic energy, and it allows the molecules to overcome their attractive forces and separate. It allows those molecules to, not the molecule itself to break down, but the connection, the attraction between water molecules to break down. And melting starts. And so you can see two phases. I see a solid and I see a liquid in that picture. Freezing is continuing, this is the kind of the reverse of melting, right? A liquid changing to a solid. So we know that things are getting colder. So that means you're removing thermal energy, which is heat, and you're lowering the kinetic energy because the temperature is lowering. And remember, kinetic energy and temperature are going to do the exact same thing. So kinetic is going down, then the temperature is going down as well. And so it's no longer has enough motion for those molecules to overcome the attractive force between the molecules, and they come back together, which is freezing. Good? Right? Evaporation, you will also sometimes see this called vaporization again. Liquid changing to a gas. So this happens two ways. If you, and this happened when I left the beakers with the alcohol and the water in them over that long weekend, and when I came back, the beakers were empty. So the surface level molecules will be able to kind of pop away and leave the liquid. And so then they're just a gas, right? They're away from the liquid and they're up in the space above the liquid. And so when that happens enough, all of the liquid evaporates, and then you have none of the liquid left. And that's what happened to us. The other way to do this is to boil it. So you can cause evaporation to happen quicker if you boil something. So it's a liquid changing to a gas. You're adding thermal energy again. So it is an endothermic, it's taking energy in. That means temperature goes up. That means kinetic energy goes up. And what's kinetic energy again? It's the energy of what? Motion, right? I see a couple of you mouth in it. Motion, good. Right, so the molecules are moving more and more and more, right? And so they're able to totally overcome any attraction between any other molecules. And that's why they're kind of on their own, they're separated. They are the wild child of our states of matter. Condensation is the exact opposite. It's the reverse of this. Things are going to start cooling off, going from a gas to a liquid. The best examples of this is if you take like a can of pop or a bottle of water out of the refrigerator on a warm day and you have it sitting, what forms on the side of the can?
Condensation.
Yeah, good guess, you're right. What do you visually see? Yeah, little droplets, right? Little, like sweat beads almost, right? It looks like your can is sweating, right? The liquid's not coming from the inside of the can to the out. What happens is the bottle itself is very cold. The air around it is warm. So the air immediately around the can gets cooler, and there's water vapor in the air. And so that water vapor that was a gas gets cooled off. Losing thermal energy means the molecules can't overcome the attraction that they had felt as a gas, and they start to come together, and when they come together, they form little droplets of that water. Right, so there's water vapor in the air, and that water vapor then condenses into little droplets, which is liquid. Not a lot of liquid, but it's still liquid. And you can see that on the can. So taking thermal energy away, and it's the cold can that's providing that cool down, right? If you have a room temperature can, like you just get it out of like the box or the water plastic, container that you buy it at the store, you just take it out and set it, and it's in the same temperature, it's not going to do anything. It's not always going to sweat. The beverage has to be cold, and it has to be placed in a warmer area for this to happen, right? And again, it's because you're cooling it down, which is removing thermal energy, which lowers the temperature. We know kinetic is going to do what temperature does, and so if the temperature is going down, that means that the kinetic energy of the molecules is going down, so they start to slow back down, and when they slow down, the attraction kind of picks up, and they are able to condense into those little droplets. All right, so let's say we have an ice storm and it knocks out our power and we're using candles. Is it safe to say that when a candle wax melts and you see the drips, is that technically considered freezing when that wax hardens again? So we're talking about, like you go from the candle, it melts, starts dripping down the side of the candle, and then it kind of stops like mid-drip and it kind of hardens again. Is that considered freezing? Kind of hurt your head a little bit, doesn't it? See some looks like, what?
I think it's considered freezing.
Any justification for that answer?
It's just got a lower freezing point than other things.
Ooh, that's what you're gonna say?
I think no.
No, not freezing? Okay.
I think it could be because freezing is when a liquid goes to a solid and it's simply liquid and turns back to solid.
Okay. I like the way you guys are thinking it through. Technically, it is freezing because it follows that definition. Usually people don't have a good explanation of why though. You guys had a good explanation. Different things have different boiling and melting points. We associate everything with water because we're around it so much. Not everything freezes and melts at 0 degrees Celsius or 32 degrees Fahrenheit, right? And so wax has a very different freezing point than water does. And so it will freeze at room temperature, right? Water does not freeze at room temperature. So technically this matches our definition. And again, we kind of put everything in like water's category, like where we think everything should freeze and melt or boil even at the same temperatures that water does. And most things do not, or a lot of things do not. So you have to kind of just think of the actual definition and then apply it to the material, kind of like Veronica reasoned out, like, well, you're going from a liquid to a solid, technically that is the definition. We don't care what that temperature is, it's happening. We see it going from the liquid to the solid, so technically it is freezing. Okay, sublimation is kind of cool. It skips the liquid phase, all right? So what happens is a solid going directly to a gas. I heard some of you say this yesterday during the practice, or like, what's dry ice? Dry ice is kind of the everyday name for solid carbon dioxide. So if you have a chunk of this solid carbon dioxide, it will foam, or not foam, it'll steam and it looks like it's smoking. This is used like in theater productions for fog, for smoke, a lot of times like in haunted houses, just to try to, show like this foggy or smoky kind of situation where you don't actually have to catch something on fire and you can have smoke. All right, so it's kind of cool. At room temperature, it will do this. It automatically will skip the melting phase. It doesn't go to a liquid. It goes straight from the solid to a gas. And so it is skipping the melting. And so that's like the chunks of solid carbon dioxide. And deposition is the exact reverse. It is a gas going straight to a solid. So we have deposition happening a lot this time of year. If you park your vehicles outside, or if you've ever noticed frost, you go outside, it never rained overnight, but everything's frosty. Well, the air temperature has gotten colder, and when that happens, the water vapor in the air doesn't turn into a little droplet like it did when it condenses. It goes straight to the solid, and so frost is a perfect example of deposition. That water that should be a liquid gets kind of deposited and spread over evenly over everything, and it leaves this frosty, misty, frozen haze on everything. So usually you would think you're not going to have ice or like crunchy snow unless it, there was precipitation. Well, there's just that moisture in the air. When you get a temperature change going from the warm, the air was warmer than the cold objects that the gas or that water vapor was touching. And so just like, like typically it's going to be like leaves and branches and vehicles, sometimes a little bit on sidewalks, if like, or even like blades of grass and things, they're going to be colder than the surrounding air, and they're going to cool that air down. And when that happens, instead of forming the droplets, it goes straight to the solid, and you have that frost. And so that's all deposition really is. But it's cool because it does the same thing though. It skips the liquid. Okay. All right. Let's look at the sublimation, because it's going to show both.
In this video, we're going to look at the sublimation of iodine.
Yeah, we're done with the notes for today.
So when we add solid iodine to hot sand, we have a hot plate underneath there, you can see right away we start getting a purple gas. That is iodine gas. In the sublimation, we're going directly from a solid to a gas without passing through a liquid phase. So you can see here that after a while, when that gets even hotter, we get a lot more of that purple iodine gas, which is escaping through the top of the beaker. So we can actually capture that gas right now. It's escaping through the top of the beaker. But we can put a piece of glass